All right, good morning, everyone. So today will be a bit different. We will do a Lab 4 primer. So we'll do, or I won't do, you will do a mini version of Lab 4. So if you can do it, the Lab 4 is not much harder than this lecture. But as the caveat, I'm not going to be doing anything. You're going to be doing it. So we're going to come up with a solution together. And this will also somewhat help for the quiz because we're going to deal with processes and make processes and do fun stuff. So what are we doing? Today, this is our task. We want to send and receive data from a process and actually communicate with it. And this will also help you if you ever need to glue things together with Python. Essentially, we are making the Python subprocess module. So our task for today, we want to create a new process that launches whatever programs in the command line argument. And then we want to send the string testing with a new line to that process. And then we want to receive any data it writes out. So we want to send data to it and get data from it. So we're communicating with it both ways. So that sounds pretty cool. How do we do that? So I'll introduce some APIs that we're going to be using today. The first one is called pipe. So, Jesus, that jackhammer is annoying. So the first one is called pipe, and it takes as an argument, oh, sorry, I missed the int there. It takes an array of two ints that fills in a file descriptor, and it's a C function, so it returns 0 on success, -1 on failure, and sets error no. So a pipe is basically a one-way communication channel using two file descriptors. So if pipe succeeds, it fills in the array of two integers, and at index 0, that is the read end of the pipe, so you're only allowed to do a system call read on that file descriptor, and then file index 1 is the write end of that pipe, so you're only allowed to call write on that file descriptor. And the way it works is anything you write to it will pop out of the read end. So that's kind of useless for a single process because you're writing data you read. But because it's a file descriptor, and we know when we fork, we can copy file descriptors, and we know standard file descriptors, we can use a pipe to communicate between two processes, as long as we do some fancy stuff that we'll be doing today. So you can think of it, if it's easier, as like a kernel managed buffer. And again, anything that's written to the write end will pop out of the read end, and the kernel will handle that for us. So we saw execve. It's kind of ugly. To make our lives a little bit easier, there's C wrappers to make our lives easier, and one of the C wrappers that will make our life a little easier is called execlp. So instead of taking a full path, it just takes a file and then an argument that's not an array, and it just ends with a null pointer. So this is the exact same as execve. It does not return on success, and it will return -1 on failure and set error no. So it skips having you use arrays, and it also searches for executable using your path environment variable, so you don't have to specify the whole stupid, path to some executable starting at root. All right. So next API we'll use is this close. That's how you close a file descriptor, so you're done with it and the kernel can reuse it. So again, return 0 on success, -1 on failure, sets error no. That will be a common theme. And it closes it. That file descriptor is no longer usable. You can't read or write on it. And then it frees up that file descriptor. Again, file descriptors are just a number, so the kernel can reuse it again. So if you close file descriptor 0, typically open will use the lowest file descriptor, so it would just replace 0. So that's one way you can fiddle with file descriptors. Another way is this one, dupe and dupe2. So it essentially makes a copy of a file descriptor. And again, this one's a little bit different. It returns a new file descriptor on success, -1 on error, and sets error no. So it copies the file descriptor, old file descriptor, and sets a new file descriptor, so they're both pointing to the same thing. So in the dupe version, we just copy we take the old file descriptor and we just get a new file descriptor back, and both old and new are pointing at the same thing. But in the dupe case, we don't get to pick what number that is. And the dupe2 case, we do. So dupe2 is also going to be atomic. So what dupe2 will do is it will take this new file descriptor argument, and if it's already open and a valid file descriptor, it will close it for you, would free up that number, and then it would do the copy. And of course, if we have multiple threads, for example, if we have to argue about stuff for like your quiz or any multi-threaded program, there'd be some race condition there if it has to close and then open, and another thread could come in and swoop that file descriptor. So dupe2 is atomic, and that's why it's a special system call. So it'll make the old FD and the new FD refer to the same thing. So any questions about this? So I just make two file descriptors point to the same thing. And with dupe2, we can change the number. All right, now we know enough to make a solution. So if you want to follow along, whatever it's in the lecture 16 directory, that's how you build it. It's already built, and we're going to create an executable called subprocess that just takes a program as an argument. And again, we want to send the string testing to it and read whatever data it writes out to standard out. All right, so there is a small skeleton. So the first thing, just make sure that we have two command line arguments. Otherwise, it returns inval, which just means invalid arguments. And here, I just set up some arrays because we'll probably need them, and create a fork. And then in the parent, I give these pipe file descriptors and the process ID of the child. And the child, I give the argument for the name of the program. So where should I start? So let's go back to our goal. Because you guys are doing this, I am not. So we want to create a new process that launches from the command line argument. So if we fork, we probably want to turn our child into that. That's probably a good first goal. And then we want to send the string testing to it and then read whatever result comes back out of it. So what should I start with? Yeah. Okay, so the comment was write some code to figure out if I am the child or parent. I did that. So I have a parent function and a child function, and when I make it, I have a bunch of unused file descriptors because I don't set them to anything yet, or I don't use them. All right, so first off, so let's see, if I want to run it with this, I expect it to, run that uname program, and then I should be able to capture whatever output it gives. So if I run that right now, oh, whoops, did I already write some code? Oh, yeah, I already started you off. There we go. So in the child, I just execute that program. So that makes sense? Cool, what should I do next?
The program is called uname.
Uname, yeah.
Uname.
Yeah, so we could execute, we could execute any program we want. What's going to happen if I execute cat right now?
It does the function.
Anything I type should come out. So if I run cat, I get input output error. Yeah, the file descriptors are still a bit messed up. I didn't do anything with them, right? So there's two things. It's trying to read from standard in, which is the same standard in as my sub process. And it's like, no, I don't see anything available to read. Yeah. Okay, so let's set up the pipe between each other. Let's capture some output first. That sound good to everyone? So if I want to create a pipe between the two and essentially share file descriptors, where should I create my pipe? Should I do it before or after the fork? After the fork. So you want me to do like here. I'll do pipe with out pipe, like that. Sorry? It is an array. It's an array of 2. Yeah, so it's an array of 2. Okay, so I'm going to just put everything. So I wrote a check error function that basically just checks if the return is -1, and then we'll just exit the program with error no, just to make debugging a lot easier. Oops. All right, so I do that. Okay, what's my next plan? So I created a pipe for an out pipe. So after here, right, I'll have out pipe FD 0, which is my read end. And then I have out pipe FD1 is my write end.
And both are.
Sorry? No, so they'll get set from the pipe call. Yeah.
Would you do it before and then when it works, it copies both, so you copy both?
Yeah, so in this case, if I have my pipe after the fork, how many pipes do I have? 2, right? After fork, I have 2 processes. So I have 2 pipes, and there's no way I can share because they have 2 independent pipes now, right? So I can take advantage of the fork. So if I move this up, so now how many pipes are there? 1 pipe, how many processes are there? 2. So I have 1 pipe and 2 processes, so then I can connect them together, hopefully, right? Okay, so that seems a bit better. So I have my pipe, and then here in the parent and the child, I pass, out pipe file descriptor and out pipe file descriptor to both of them. So they both have, in those functions, they can both access both of the file descriptors. But there's only going to be 1 pipe here, and it's the same for processes, because whenever I forked, it copies, they're exact clones of each other that are independent, but all their file descriptors are the same, and file descriptors are essentially pointers, so they have all the same file descriptors. Sorry?
Or just change the pointers to like 2 processes to share a pipe and to do a mutual communication.
Yeah, so they're kind of, so there's 1 pipe. So first we're just going to deal with getting output from that process. So we have 1 pipe, we have 2 processes, and we just need to connect them together somehow. Yeah.
But when you do fork, don't you copy everything?
Yep.
So don't you have 2 pipe but same?
But I forked after the pipe.
So the things before the fork it's not copied?
So it's when you create a new process, everything's the same thing at the time of the fork.
Oh, okay.
Right, and this is how it's going to work. This is how it's going to work on quiz 3 too. So everything right before the fork, at the time of the fork, they're exact copies of each other, with the only difference being the return value of that fork call. So right after the fork, I will have 2 processes. 1 will come into this and call parent, and then 1 will come into child and call child. But at the time of the fork, they're going to be independent, or they're going to be complete copies of each other. So because I create a pipe before the fork, they both have those file descriptors. So this would be, if I want to give them a number, there's going to be the standard file descriptor 0, 1, 2. So this one's going to be file descriptor 3. This one's going to be file descriptor 4, like globally, because it just uses the lowest number. So after we fork, both processes are going to have the 5 file descriptors. They're going to have the 3 standard ones and then 2 from the pipe. Yeah.
If out pipe FD contains both the in and the out file descriptors, why do we need in pipe FD?
So we're going to, why do I have in pipe FD?
Yeah.
So we're going to be giving data to it and then reading data from it. And they're each going to be pipes. They're all one way. So I'm going to have a one way into the process and one way out of the process. So we're just going to deal with the one way out of the process first. Yeah.
And when you initialize output FD, it's just 0?
Yeah, so I just initialized it at 0, but it gets updated due to the pipe call. So the pipe, it's going to use, the pipe FD argument and then update them if it's successful.
And 3 means the terminal. If you get file descriptor 3.
No, so by default, whenever you create a process, right, there's the standard file descriptors. There's file descriptor 0, 1, and 2. And then the way Linux says, if you open new file descriptors, you just get the lowest number first. So pipe's going to open 2 new file descriptors, and it's just going to do lowest first. So I know that this is going to be file descriptor 3, and this is going to be file descriptor 4.
So where is file descriptor 3 pointing to?
It is pointing to the read end of the pipe.
Can we just let it read and point to the standard out so we can read out?
Sorry?
So can we let it read to point to the standard output so we can read from?
Yeah, so the comment was, can we make the read end point to standard output? That's close. So what do you typically do if you're a process and you want to write some information out, or you want to say hello world or something like that? What did we do? What system call did we use?
Right.
Right. So if we want to capture the output, then what we would want is for the right end of the pipe, the child process, that end of the pipe should be its standard output, right? So it would write to that, and then in the parent process, we should be able to read from that to get data out of it, right? And that's our one-way communication channel. We want to send that process's standard output to us, and we want to read from it. So we can do that with a combination of dupes. So in here, if I want to do that, so I could do a dupe if I want to overwrite a file descriptor. So let's say I want to overwrite, which file descriptor am I trying to replace here if I'm trying to capture its output? Standard out. So I should probably replace standard out, and this is it's just a little bit more readable than seeing 1. I wouldn't really care if you put 1. But here, so what file descriptor do we all want to replace with standard out? Out pipe FD 1, right? So if we do that, that's a little bit closer. So now this would essentially it replaces the original standard out, which would be the terminal or something, and replaces it with the pipe FD, and then overwrites whatever was file descriptor 1 originally. So if we do that, let's see what happens if we write uname. So if this pipe is connected, should we see output now? No. Cool. So we did something. That's cool. We should probably check that if we have errors or not. Oh, there's comments in chat too. Cool. Yeah, so pipe's just a one-way communication channel. All right. So let's make sure our dupe didn't have any errors. So it doesn't have any errors. We're capturing it. And we should be nice and clean up all of our file descriptors. So we should also just check error. We should probably just close out pipe FD 0, close. Oops. So this way we can clean up all of our file descriptors. So let's read through it again. So at the time of the fork, we have 5 file descriptors. Yeah.
Quick question.
Yep.
So you know when you're closing the file descriptor, right?
Yep.
Why are you closing it as soon as you switch to output?
So I don't need it because now there's 2 file descriptors pointing at the pipe. I don't need file descriptor 4, for example. So here let's go through it. So here at out pipe FD, I have 5 file descriptors open, right? So I have the default 0, 1, 2, and I have file descriptor 3 and 4. Okay, so then the fork happens, so both processes have the exact same set of file descriptors. Let's argue about the child. So if we go in the child here, it would be a dupe 2 of what I say that was, 4. So this makes FD4, 4, and FD2 point to the same thing right after this line. So at this point, I'm just cleaning up my file descriptors. So this would close FD3, and this would close FD4. And that way, it's nice and clean. So my new process, whenever exec happens, it just has this 3 standard file descriptors. It doesn't have any additional garbage open. And we're going to see why this is important quite soon. But yeah.
Will you close your like the standard output, because 4 is pointing to standard output, and will you close your standard output?
No, so if I close 0, then when that process spawns, 0 will be an invalid file descriptor.
Isn't that what you try to do there?
No, I never closed 0. So I overwrote 0 in this line, and then I closed additional ones. I never closed 0.
You close 4?
I closed 3 and 4.
And 4 is pointing to standard output?
So 4 and 0 are pointing to the same thing.
But you kill 4 itself. You just kill the pointer.
Yeah, I just killed the pointer. So now I just have one file descriptor pointing to it, and it's the standard out, or standard out, yeah.
I get why we close 4, but are we closing 3 because we're just not really going to be using it?
Yeah, we're being nice. Yeah, we're very nice programmers here. Okay. So we don't see any output. That's a good sign. So how do I read whatever the hell just happened? How do I get that output back out of it? Yeah, so I'm communicating with the parent, so I should be able to get data somehow. So what should I do here? A for loop? Sorry?
Wait, for parent, do we want to print out what the other process sent to us?
Yeah. We want to print out what the child sent to us. So it dumped information to the pipe.
Can we do the standard out of this to the out to the pipe just to kind of redirect?
So, okay, let's. Oh, yeah, that's the class dog. So what do you want to do? Sorry.
I think we change the standard out of the child pointing to the pipe. Can we change
So let's see.
can we change the standard out of?
So here's our pipe. Oops. Right, and this is write, and this is read. So in here we have the child, and then we have the parent. Okay, so the way the child is the child's file descriptors are 1, 2, 3, after we clean them all up. And then we leave this alone, original, and then file descriptor 1 points to out, pipe FD1, which is essentially this. So it's filling up that side of the pipe. Okay, and then so in the parent, what do you want to do? Sorry? Sorry, you,
Is there a way to redirect out pipe FD at 0 to standard out so that we print out whatever's coming out of the pipe?
but we want to capture it. What about if we want to do something with
We
it?
just want to capture it.
Yeah.
What's the
Sorry, standard
standard in?
in? So in the parent, I have, so here I have 1, 2, 3, so these are all original because I haven't screwed with them yet, right? God damn, I have to stop saying. These are all original, and then I also have out pipe FD 0 and out pipe FD 1. Yeah.
Do you connect your standard in to out pipe 0?
Connect my standard into out pipe 0. Yeah.
Can we just read from out pipe FD 0?
Yeah, that seems logical, right? Why am I? We don't want to touch the parent's file descriptors. They're all good. It's a file descriptor. We can read from it. So, what happens if we just read from it? All right. Who wants to tell me how to read from it? Read. Okay. Whoops. Read.
That's good, just compile that.
Let's see. Oh. Ah, semicolon. All right. Whoops.
Sorry, you have to add please.
Hey, that compiled. Statement with no effect. Yeah, that compiles. Yeah. Yeah, I mean, why wouldn't that work? Can I do this? Null semicolon? I can do that. Read's just a function pointer. Yeah, I mean, but if we just do read, the compiler gives us a nice warning. It says statement with no effect. So I mean, it's not going to do anything. But I mean, it's cool. It runs still. It compiles. So read. So it needs a file descriptor. What file descriptor we want to read from? Out pipe FD 0. So that's the read end of the pipe. So if the child process is writing to the pipe, anything it writes to the pipe comes out of the read end if we read it. Okay, it needs a buff and size T. Help. My brain, I hit my head this morning, so I don't know what to do.
I guess you just choose make a buffer 1024 bytes.
Buffer 10, okay, we'll use this magic number. All right, so we'll use this magic number. Yeah, so that's the question. Do I have to check if it's ready first? Like, what about if I get there before it writes any data? And, well, is read a blocking system call? No. Yeah. Yeah, so read will just sit there until it has data. Remember our example that just read and wrote? It was essentially cat. It just waited for data, right? It just waits there. So that's fine. So that should be fine if we wait there. So read needs a buffer and then size of buffer. All right, so that's missing a bracket. All right, that's kind of cool. So what should I do next? So that seems to compile. It did something.
In the case that it's greater than 496, wouldn't you need to just keep reading until like if everything is read from the file?
Yeah, so there's something So we'll take a little bit of shortcut. So if you had to read more than 4,000 bytes, you'd have to do multiple calls and do the buffer. We'll assume everything's pretty short and fills that. So we'll be a little bit lazy, but in general, you should do better than this.
After you read, do you want to output to the command line?
Yeah, although first I should probably check my errors, right? So I don't even know if this is valid. I'm just throwing it out. So what does read return? Anyone off the top of their head?
Size that you.
Number of bytes read, I heard. Okay, bytes read. Okay, well, I should probably check my errors because it returns -1 if it's invalid. So I'll just do my check error function just to make sure. So check error again, just checks if the return value is -1. If it's not -1, it just returns, it doesn't do anything. If it is, it captures the error no, prints the message with whatever you give it, and then exits the process. So here, let's check that we actually read something. So that's still good. Hey, it didn't crash or do anything. It's pretty cool. Let's check, printf. And I'm allowed to do printf because I didn't screw with the parent's file descriptors. So I can still do printf because remember we know printf, it just calls write on file descriptor 1. So if I screwed up file descriptor 1, I can't use, if I printf, it's just going to go to the pipe and then go off to some nether regions. So this is why in the parent, I did not touch them. So here, I read, let's see, was it ULIT? I think that's the right format. Bytes read. Or maybe it's LD. Type has int. Oh, okay, it's just an int. Well, I'm just seeing the number of bytes read first. So I read 6. Seems right. Because if I run it, it's Linux, 1, 2, 3, 4, 5, and a new line. So I read. So we have some evidence that we actually read something, and we read something from another process. It's kind of cool, right? Well, let's just write out whatever we wrote. So I'll give you the shortcut for this. So this is a weird format specifier. So this is if it's not a C string. So it is $.*s. So by default, you kind of know what this means, right? $s, it's a C string, but is the output from this process a C string? No, we have no idea if it ends in a null or not. So this format specifier just lets it be a string, and you have to say the length of the string. So the length of my string is the number of bytes I read, and then buffer. So then I can got. So I'll just output the string from my buffer given the number of characters I read. So if I do that, my parent process should have actually captured the output from essentially the sub-process or the child. So if I do that, got Linux. Wow. So we actually are communicating between processes now. It's pretty wild, right? Yeah.
And that's done by the pipe. In the child process, it puts something to the terminal, which is file descriptor 1.
Yeah.
Put to the pipe, so you read from the pipe.
Yeah. So how this worked? Is we created a pipe. So we created a pipe. So it had a write end and a read end, and then we forked. So now we have two processes, a parent and a child. They both have the same pipe. All the file descriptors are copied at that point in time. Then after that, they're all independent. So in the child, what we did is we replaced file descriptor 0 with the right end of the pipe. So now whenever that program prints the standard out, it's just going to do a write 1. And now instead of write 1 being whatever's the default, we set it to the pipe. So whenever it writes to standard output, it's actually writing to our pipe now. And then we're just nice. We close the extra file descriptors so that that process just has the 3 standard file descriptors open and not some additional garbage. And then after we exec, after we exec, it just starts running that program. It does a read on file descriptor 0. In this case, it doesn't use standard input. It just displays some message. And then it writes to file descriptor 1, like standard out. So it writes to the right end of our pipe, and then in our parent process, we just simply read that data. So we're communicating between 2 processes here. That's our one-way communication channel out. Okay? Who wants to guide me through the next one? So next one, we want to send the string testing with a new line to that process. Yeah, so another pipe. Luckily enough, I already created an in pipe FD. So that's pretty good. Should I create my pipe before or after the fork? Both. Oh, you said before. Okay. Okay. All the jackhammers are screwing with my hearing. Okay. So now we have 2 pipes. So we already set up the out pipe properly because we're set it up so that we read from it, and then we set it up so the child writes to it. So for the in pipe, we should be doing the other way around. So the child should be reading from it, and we should be writing to it to form that communication channel. So let's deal with I'll remove these, and let's deal with the child first. So what should I do for the input pipe in the child? Whoops, pipe, not pi. Pi would be good though.
Connect the,
Yeah, go ahead.
connect the standard input to the pipe.
Yeah, so I want to connect the standard output, so I probably need a dupe2 call because I know I want to replace standard input, which is just going to be 0. So what's replacing standard input?
The write.
Sorry, in pipe FD, which 0, right? That is the read end of the pipe. So whenever this process executes, whenever it reads from standard in, it would be reading from the pipe. Okay, and then we want to be good and close our additional pipes. S out. Whoops, why am I recording a macro? Stop. All right, so now we fixed our pipes. Cool. Well, now we still have a bunch to do. Okay, so now we want to write information to that pipe. So this was okay. Well, if I want to give that process some data, what do I want to do? Just write, and I should write to it first before I read from it. Otherwise, that doesn't make too much sense. Hey, write to the pipe. Whoops, write to the in pipe. So let's be specific, and then read from the out pipe. So const car message. So our message was going to be testing with a new line. Okay, well, I want to write to it. So I should probably check bytes written, and then I'll do the write system call. So what file descriptor do I want to do here? in pipe FD 1, right? So that's the right end of the pipe. And then I need a buffer, so I want to print the message, and the size is whatever the string length is. So that should do that, and I will check for error, check error bytes written right, just to make sure. So if I execute it now, and I use subprocess with, if I use uname, it doesn't matter, it's not gonna read anything anyways, right? So more interesting is probably cat. So if I do that, got testing. So I wrote testing to it, and then I read testing from it, because cat just doubles whatever. So everyone get that? Okay. So we have forgot something. Sorry? Set exit? It stops earlier, so it does stop a bit earlier. Are we good parents?
We didn't kill the children.
We don't want to kill it. We want to wait for it. We create a zombie, so we should actually be fairly nice. So if I want to wait for it, I can actually, where do I want to wait for it? Yeah, after the write and before the read, probably. So I just let it finish, and then I'll read whatever data it has. So how do we be good parents? So yeah, we can do wait PID. So if we want to do wait PID, we need somewhere to put it. So wait PID, it wants a process ID, which is child PID. So, and then stat location, so that's W status, and 0. So we want to wait PID for it. And then we should, of course, check error.
Well, what's W status again?
So it takes a int pointer and sets it to the status of the child whenever it exits.
Oh,
So, yeah, so man. So if we look at it, we call wait status. Wow, this suspends. Okay, that doesn't help. Essentially, it just writes the exit status there, and then you can check it. So first, we'll write some asserts. W if exited, so this is just stuff you'll know from the beginning. So we want to make sure that the process has exited, that it's exited. And then if we want to get its exit status, we use W exit status. So that gets its exit status, so we can double check it actually exits properly. So what's an exit status? That means everything's all good. 0. So we should probably just make sure that our program's all good and nothing bad has happened. So let's do that. So now, when we do this on cat, uh-oh, SpaghettiOs. We broke something. So I have to control C, and it's sitting there. And the cat's still not running, but we broke something.
both processes are blocked.
Our wait's in the wrong spot, so no, our wait's not at the wrong spot.
Maybe after you wait after read.
Wait after read.
That's
I could, but I don't want to. So what is if it's cat, what's it going to do? It just reads over and over. When does it stop? End of file, or when read is 0 or it's closed. Did we close it? So in the parent still has the right end of the pipe open. So how does cat know it's done? If I still have the file descriptor open, it doesn't know what your process is going to do. You could write data to it at any given time. So after I write to it here, what should I probably do? Close. So let's check error, close. And what should I close? One. Close. So now if I close that, that means, hey, I'm done. I close that file descriptor, and it should then be able to send, that end of file thing, which is just read returns 1, which essentially just means it's done. So that file descriptor cleanup is going to be a fairly important thing in Lab 4, because you're going to be essentially this, right? If I do this over and over again and type, that has what? 3 pipes in it? That's Lab 4. So if something freezes, then it's probably you didn't handle your file descriptors properly. So here, I'm actually fairly messy with my file descriptors. I could be a little bit nicer, where at the beginning, which ones do I know for sure I'm not going to use at all? Well, I don't use this one at all, so I should probably close it. And I also don't use outfd. I don't use outfd1. So I don't use the right end of the pipe. So those are 2 ones I don't use. I should just close them immediately just to keep things clean, so I don't have this stupid issue where, file descriptors stay open and it just kind of looks like it hangs there because it's waiting for data. So I cleaned up in pipefd0 and cleaned up in pipefd1. Then I cleaned up out pipefd1. I should probably clean up out pipefd0 just to be complete. So I'm done with it here. So I should probably close it right after I'm done with it. So now I'm clean. So here in main, I created 2 pipes. And then, in main, I created 2 pipes. I can delete this now. I created 2 pipes, and then the child, I closed all 4 of them. So all 4 file descriptors. So I closed them here after I shuffled them around. And then in the parent, I also closed all 4 of them. So I closed the ones I know I'm not going to use immediately. And then I closed the write one right after my write call. And I closed the read one right after my read call. So I cleaned up everything nice. And this is kind of why they tell you to, make sure you malloc on free, because for some things it's very important. So now if I do this, subprocess, cat, cool. And also the uname one works as well still. So you're just sending it data and it doesn't care. But I can run a whole bunch of other stuff. ls works too. I can capture everything from ls. I don't know. So true is also a program that doesn't do anything, just sets a 1 as an exit code. So that's fine. Then false. Oh, well, false, it always exits with error code 1. So triggers that assert. So that's pretty cool. And then as the next thing that I'll leave you off of to fix is, hey, what about if I do, something like this? Invalid. It kind of failed silently. Why would it fail silently? Yeah.
Because since it's invalid,
Yeah, but why can't I see that a problem happened?
What does invalid do?
So it tries to run the program called invalid, which doesn't exist.
Oh,
So I could also, instead of invalid, I just do. All right, well, we're at time anyways, but that's our solution. So we'll,
That is like we equate something to the standard error, like we can capture it.
close. So you'll have to fix that in lab 4, but lab 4, if you understood this today, you just do it a bunch more times. So if I do cat, pipe, cat, well, I'm creating 3 processes, 2 pipes. I'm just connecting this to that, and then this to that. That's our one-way pipe. Cool. Well, let's remember, I'm pulling for you. We're all in this together.